Namaskar friends, I hope you are doing well. Today we are going to start with our lecture series for basic organic chemistry, the lecture number 3. First we will have a slight the revision of the previous lecture, that is lecture 2, in which we had done functional groups in detail, where we have taken individual functional groups, then their prefixes, their suffix, what are they known as, and after which we had also seen electronegativity. What do you mean by electronegativity? Electron withdrawing effect, which is electronegativity. Then we had also seen homolytic fission, heterolytic fission, right, in our previous second lecture. So for more once again revision, you can see the previous lecture also, which is already present in my playlist. Now, today we will start with a totally new topic, which is first we will do electronic effect. Electronic effect. Now, what do you mean by electronic effect? As we know, for formation of a bond, electrons are required, either by sharing mostly to get a covalent bond, right? So that means there are flow of electron between a bond in an atom, and both the atoms have difference in electronegativity. That means one is more electronegative than the other. Take for example CH3 dash. If I say, take for example NO2, as we know this is known as nitro. This can be written in a more. No. And we know nitro being a unsaturated compound, sorry, functional group. Nitro is a unsaturated functional group. That is, it has only double bonds. It has presence of a double bond. And as we know, we have seen in the previous lecture, if there is a presence of a double bond, that means it is a electron withdrawing group. So we can say nitro is an electron withdrawing group, EWG, electron withdrawing group. Now, so we can see that means nitro is going to pull the electrons towards itself, right? There will be a flow of electrons. So can I say it will be most negatively charged and this will be positively charged. So I can say poles are generated, So such type of compound, I can say there is a polarity. There is a formation of polarity. Polarity means poles being generated. Now, as we know, these poles are generated only when the atoms or when two atoms have difference in electronegativity. As I told you, electron withdrawing group means electron attracting, as the name itself suggests, and one is electron donating group, which is electron accepting. Electron accepting. Okay? Now, electron withdrawing group, as I told you, it is unsaturated. That means it should have double bond. And electron accepting means it will be all saturated. Saturated means it will contain only and only single bonds. Single bonds, or the other name of single bond is known as sigma bond. This will contain both sigma and pi bond. But pi bond is a compulsion. Pi bond is a compulsion, as we have seen here. This is sigma bond and this happens to be the pi bond. Right? Now, so two poles are generated, therefore it is known as polarity. Now, this is known as electronic effect. That means, can I say what exactly is electronic effect? Electronic effect is nothing else but effect of an electron in a bond, due to which bond between atoms which have different electronegativities. Okay? And thus, due to this electronic effect, results in formation of a polarity, and this polarity is a very important factor why a chemical reactivity takes place. Why does a chemical reactivity take place? Right? Now, in this electronic effect, there are many different effects which are known as electronic effect. First one is known as inductive effect. Inductive effect. Right? Now, what do you mean by inductive effect? As we know, covalent bonds have different electronegativities. Different electronegativity. That means, can I say if there is a difference in electronegativity? There is a difference in electronegativity. In electronegativity, I will say En, electronegativity. Now, difference in electronegativity. And so we can see the electrons will shift in a bond either towards more electronegative element, or it will just electron withdrawing group results in attracting electron towards itself. Electron attracted towards itself. Thus fractional charges, you can say fractional positive and negative charges are developed. Fine. Now, developed at the respective atoms. At the respective atoms. The can I say displacement of electron, due to electron withdrawing or electron donating group. Electron donating group is called inductive effect. Right? Make a note of it. Electron withdrawing group is electron attracted towards itself. So a fractional positive or fractional negative charges are developed. That means, in short, we can say it's polarity at the respective. And this displacement of electrons due to electron withdrawing group and electron donating group is called as inductive effect. Right? Yeah. We'll move further now. So on the basis of it, we have two types of inductive effect. One is plus I effect or plus inductive effect. Okay? And the other one is minus I effect or minus inductive effect. minus inductive effect. What do you mean by plus inductive effect? Plus inductive effect is nothing else but electron donating groups. Electron donating groups or atoms. Electron donating is known as plus I effect. And what do you mean by minus I? Means electron withdrawing or attracting groups. Fine. Now we will see some of the examples of first plus I effect groups. Now generally we can say plus I effect is shown by saturated groups. Saturated groups. That is single bonded. That is single bond. Single bond. For example, you can say CH3, yeah, फिर CH2 CH3. That means I can say this is methyl. Right? I had told you, if you remember, alkane minus one hydrogen is known as alkyl. This is ethyl. In general, is alkyl. Fine. OH group, that is hydroxy. Then we have NH2, which is known as amine, because NHH. So it is all single bonds. The NH2 OH is NH2. Then hydrogen also is electron donating. Then we can say all the alkyl groups, no doubt, as I initially have told you. Now some more examples are there, but as we go further we will come to know. We can say in alkyl groups, within the alkyl groups, the butyl, larger the group, butyl group is more electron donating than propyl, which is more than ethyl, and which is more than methyl. Fine. Means more the alkyl group, butyl is 4 carbon, 3 carbon, 2 carbon, 1 carbon. More the alkyl group, more the carbon atom, more the electron donating effect. Yeah. That means I can say, you can say tertiary carbon atom, secondary carbon atom, and primary carbon atom. Tertiary carbon atom, secondary carbon atom, and primary carbon atoms also. Tertiary carbon atom means this carbon atom bonded to one carbon atom bonded to 3 different carbon atom. If you remember in the lecture 1 I had showed you, because this is bonded to 3, so this is tertiary. Similarly, C, it is bonded to 2 carbon atom, so it becomes secondary, and this is bonded to only 1 carbon atom, so this is primary. So I will say tertiary is more electron donating than secondary, which is more electron donating than primary. Fine. Now similarly, this is indication for similarly, minus I effect groups are unsaturated. For example, you can say NO2, you can say CN, you can say CHO, you can say ketone, or you can say COOH, acid. You can say CONH2 amide. Fine. Then you can say COCl, acyl chloride, COCl. Fine. Now we will see the this. See, even NH4 is a electron withdrawing group. NH4 in the sense ammonium. NH4 in the sense ammonium. So, and ammonium is the most electron withdrawing group. So I will say ammonium is most, then NF2, which is most, then CN, which is most, then SO3H, which is most, then aldehyde, then ketone, then acid, that you can say, see it is COCl, okay, then it is COOR ester, then it is CONH2 amide, and then it is the halogens. That means fluorine is more than chlorine, is more than bromine, is more than iodine. Although OH also happens to be somewhat electron withdrawing, and then happens to be OR, which is known as alkoxy group. Alkoxy, if you see my functional group lecture, in which the alkoxy OR we have seen, and similarly this is the hydroxy OR. Although they are very poor electron withdrawing group, but yeah. Now you can say after this, even you can say then NH2, then pH. pH is nothing else but phenyl. Phenyl is what? This bonded to somebody, phenyl, and this is then H. So don't get confused that this is saturated. These are the few saturated ones who are also electron withdrawing, although very weak electron withdrawing groups. Mostly their habit is of electron donating. Okay. Different applications of inductive effect. Fine. First is effect on the acidity. Acidity and basicity of a molecule, or acidity and basicity of a molecule, or you can say acidic and basic strength. And basic strength. Now, as I have told you, electron withdrawing group is -I effect, and electron donating is +I effect. Fine. Now we will see an example. CS3, C double bond O, OH, which is acid. COOH, acid. Now I know this is an electron withdrawing group. So this is going to pull electrons towards each other, towards itself. That means I will say this is an electron withdrawing group. That means I will say it's a -I group. Yeah. The moment it will pull electrons, then here there will be a partial positive charge on the carbon atom, and there will be a partial negative charge on this carbon. Fine. Now hydrogen, we know already it is already partially positive in nature. Now if two positive are near to each other, then obviously there will be a repulsion. There will be a, as we know, repulsion between two positive charges. Fine. Between two positive charges, that is positive carbon atom and positive hydrogen atom. If there is a repulsion, that means this hydrogen atom can be easily knocked off. It can be easily knocked off, removed. And we know a loss of hydrogen atom is known as acidity. Is one of the definition of acidity also. Loss of hydrogen atom is also known as acidity. Okay? Now similarly we can say, therefore this is methyl and CH. Methyl, this is nothing else but acetic acid. It is known as acetic. Therefore acetic acid is acidic in nature. Okay. Now similarly, even the presence of a secondary functional group, a close functional group which is in close proximity, it is near to the carboxylic acid, also affects the acidic and basic nature. For example, I will tell you. Suppose we will take, this is number A. Fine. Now we will see the different. Now we will see, suppose CH2COOH, which is chlorine, then CH2COOH, which is here the another function is fluorine, and you can say, yeah, so I will say this is B and this is C, and we know F is more electronegative, is highly electronegative, so carboxylic acid will pull electron towards towards itself, and fluorine also will pull electron towards itself. That means here the positive charge on the carbon atom, which here it was only due to the carboxylic acid. Now the positive charge on this carbon atom will be much more, which will be much more. Fine, because the electron is being pulled by the fluorine atom and by the carboxylic acid itself, right? Although now chlorine also is an electron withdrawing group, right? But it is more poor than with respect to fluorine. So the positive charge will be smaller positive charge, although bigger than A. The concentration of positive charge on B will be more than A but less than C. Sorry, this is C. This is C. Fine. So I can say in terms of acidity, C is more acidic than B, which is more acidic than A. Fine. Because in C there is fluorine, which is highly electronegative, so it will pull electrons, and even carboxylic acid will pull the electron. So the concentration of positive charge on carbon atom which will be more, and we know hydrogen atom is already positive in nature, so it will easily be knocked off. Hydrogen atom will be easily knocked off. Similarly, chlorine, although it is also electron withdrawing group, but its effect is weak as compared to fluorine. Fine. So here the concentration of positive charge will be a little less than fluorine. Yeah, molecule C. Okay. But this B will be, here the positive charge at B will be much more than the positive charge in A. Fine. So fluorine, that is C, will be more than B, which will be more than A. Fine. In terms of acidity. Right. And similarly, if I want to say, as we know, here fluorine is their positive charge. Okay. So I can say the other way around. A is more than B is more than C with respect to basicity. Fine. Here the positive charge is there, no doubt. But here to retain the hydrogen capacity will be much more, which will be much more to retain it. It will not try to leave off. It will not try to give it off as compared to fluorine, which will want to give off the hydrogen atom of the carbon atom of the carbon. So in terms of basicity, I will say A is more than B is more than C. Fine. Now we will see another effect. It is the effect of distance. Effect of distance. Now, what do you mean by this? Take for example CH3, CH2, CH2, COOH. Fine. Take this A. Similarly, CH2, 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 COOH, CH2, CH2, COOH. Here it is chlorine. This happens to be, suppose B. CH2, CH3, then CH2, which happens to be chlorine here, then CH2 and then COH happens to be C, and here CH3, CH2, CH, here happens to be chlorine, and here then COH. Now I can say chlorine is also electron withdrawing, COH also is electron withdrawing. So the density on this carbon atom, the density of positive charge will be much great. Now, as the distance increases, distance of the chlorine with respect to carboxylic acid increases. So no doubt the electron is going to be pulled by chlorine, but the density of positive charge here will be less. Fine. Similarly, here it is, this chlorine is situated on the, here it is on the first and second. Here it is based first, second and third. Here it is 1, 2, 3, 4 on the fourth carbon atom. So here the positive charge will be much less. Fine. And here, although there is, here since there is no halogen, no chlorine, so here the positive charge will be still more or less. So I can say easily that A, B, C, D, suppose this is D, I can say D is more than C, which is more than B, which is more than A, in with respect to acidity. So the distance of chlorine matters now. Here the chlorine is just next to carboxylic acid, which is already electron withdrawing. This also. Here chlorine is on the third carbon atom. Here the chlorine is on the second carbon atom. This is on the fourth carbon atom, and there is no chlorine atom. Fine. So this will be most positive here. This will be a little lesser positive. This will be another very this, and this will be very small. Fine. The second was, now first we saw the effect on the acidity or basic strength. Then second was effect of the distance. Now the third happens to be stability of carbocation. In our previous lecture, we have seen what do you mean by carbocation? A carbon with a positive charge. A carbon with a positive charge. Take for instance, this is a carbon atom which is bonded to some electron withdrawing group. Suppose if I say electron withdrawing group. So what will happen? The electron will move towards G. So we will get C plus G minus. Okay? So now this is a positively charged. This is known as the carbocation. Cation means positive charge. This is carbocation. Now, if I want to see the stability of any molecule, it should be neutral. As we know, it should be neutral. So, if the positive charge is there, then the molecule has to be unstable. So, any electron donating group, right? Any electron donating group, if it continuously donates electron, the positive charge is obviously going to diminish. It's going to become lesser and lesser. Fine. Now an instance will come when there is no more positive charge. That time it will gain the stability. Fine. So a positively charged carbon atom can be stabilized by an electron donating group by attaching it to electron donating. Take for example R and R. Suppose this is a positive. Now similarly here R, C, R, here there is a H and positive, and here there is R, C, H and positive. Now here positively charged, but it can be stabilized by 3 different alkyl groups, and as we know, alkyl groups are electron donating. So I can say this is a tertiary carbocation, this is a secondary carbocation, and this is a primary carbocation. So I can say tertiary carbocation is more stable than secondary, which is more stable than primary. Why? Due to, this is the stability. Why? Due to the presence of electron donating group. Fine? Electron donating group. And similarly, obviously no doubt about it, methyl will be the least. This goes without saying. Methyl will be the least. Fine? Yeah. So it will be, I can say like that, then like that, and then like that. Fine? Now, similarly, stability of the carbon atom. The story remains the same. Suppose if I take R, C, R and R, this is minus charge. R, C, R, H and minus charge. And R, C, H minus charge. And C, H, and minus charge. Now, since this is minus charge, so it will require a group who is either electron donating group, electron withdrawing group. It should have an electron withdrawing group, or the effect of the electron withdrawing capacity has to be more. Now, if I take the same example of R, This same example I want to replicate here, so that for you to understand is becomes easy. Same way. Now here, since R is an electron donating group, so if it continuously donates electron, the negatively charged will be becoming more. It will be increase in concentration of the negative charge. So obviously, as we know, the presence of a charge on a particular molecule increases the instability. Increases the instability. Here, the negative charge will be relatively lesser than this. This is tertiary. This is secondary. And this is primary. And this is the normal methyl. Fine. And here it will be it's very less. And here there will be no electron withdrawing group. So the negative charge here will be least. This here will be more. Here it will be much more. Fine. So can I say for carbon ion it is the opposite way down? That is methyl, which is more stable than primary, which is more stable than secondary, which is more stable than tertiary. Effect. First effect was the inductive effect, right? In that inductive effect, we saw the plus I effect and minus I effect. Fine. Then we saw the applications. Now we will see what exactly happens due to the inductive effect. Right? Now, I can say inductive effect is thus first a permanent effect. I will say it's a permanent effect. It's a permanent effect because the presence of electron withdrawing and electron donating group will be always be fixed. It will always be present in throughout the molecule, right? So that means it is not dependent on some other reagent or any other molecule, any other chemical which has to be added, Fine, this is a permanent effect. Now, this operates only across sigma bond, or I can say single bond, or I can say saturated compounds, alpha sigma bond or single bond, sigma bond or saturated. Fine. Then the inductive effect, the effect is more prominent till the third carbon atom. That means, suppose something G is there. Either it will be electron withdrawing group or electron donating group. But the effect of G, maximum it stays only till first, second and third carbon atom. And if there are, suppose, more than 3 carbon atoms, that means I'll say this is the fourth, the effect diminishes, starts decreasing. That means it is there, thus the inductive effect is there only till third carbon atom. So I can say it is a weak effect. It is the weak effect. Fine. Yeah. There is something. Now another effect. After inductive effect, another one is known as resonance effect. Now what do you mean by resonance effect? I will say it is a polarity. It is polarity generated in a molecule. In a molecule due to interaction between lone pair of electron and a pi bond, that is double bond. Fine. I will say polarity generated in a molecule due to interaction between a lone pair of electron and a pi bond. For example, I will show you. Now, take for instance R C double bond O dash H. Right? Here there is oxygen has two lone pair of electrons. Fine. Then I can see this will go here. It can form a bond. And the moment it goes here, the carbon, one bond has to break. Because if it goes here, C double bond O, then carbon valence is 4 as we know. If C double bond O, then it can't be double bond O again here also. So it has to become a 1. Therefore, that means there is a shifting of pi bond. The electrons of the pi bonds are shifted. RCO minus. You can see, right? Fine. Now, similarly, again, same thing will happen. This will go here, and then again this will go here. Then to give the same compound. RC double bond O. Fine. Yeah. So we are this is A and B. Basically speaking, this and A, that means this structure and A happens to be same, right? So these two are known as canonical structures. Canonical forms of canonical structures, or you can also say resonating structure. Resonating structure. Canonical structure or resonating structure. Now you can see that molecules having, you can also say that molecules having conjugated double bond. Conjugated double bond. What do you mean by conjugated double bond? Conjugated double bond is double bond followed by single bond, again followed by double bond, again followed by single bond. Take for instance, double bond, molecules having conjugated double bonds, or it is also seen, or this resonance effect is also seen in molecules having at least one pair of electron and one double bond. Right? This has a pair of electron, lone pair of electron and a double bond. Fine? Yeah. Now as I told you, conjugated double bonds. See, it can be, sorry. C, double bond C, single bond C, double bond C. Fine. So double bond, single bond, double bond, single bond. These are known as conjugated bonds. Fine. Now we can write the resonating structures. I will write like that. Shifting of, if this goes here, then this has to go here. Fine. Then this will be C, like that. This, double bond C, single bond C. This is minus charge. This happens to be the plus charge. Fine. Similarly, no doubt, we can say this will go here, this will go here. Fine. So this is between the conjugated double bond. Okay. Now we will take one more example. Take for instance, this is the carbonyl. Fine. C double bond O carbonyl. I will say if this goes here. Fine. So this will be like that. Single bond O. This happens this, and this. So this will be minus charge. Fine. This will be minus charge. Now we'll see in some carbocation also. If there is a carbocation, suppose take for instance CH3 CH plus charge dash CH double bond CH2. Fine. Now here also we can have a conjugation, this resonating structure. How it will be? This will go here. Fine. Now CH3 CH double bond CH single bond CH2 plus. Fine. So the positive charge here and positive charge here. Now this is nothing else but a secondary carbocation, and this is nothing else but a primary carbocation. This is nothing else but a primary carbocation. Fine. And as we know, secondary carbocation is more stable than primary carbocation because it is positive charge. It wants electrons. That means any electron donating group will result in stability. It's CH3 which is electron donating, so this will get easily stabilized. Here it has a CH which is also electron donating, but the effectiveness of CH as an electron donating group is much below CH3. So secondary carbocation is more stable than primary carbocation. Fine. Single structure in resonance it indicates that a single structure in resonance, it indicates that a single structure, it is not possible to express the properties properties. The properties. Now, so as we saw in resonance, there are different resonating structures being formed. That means canonical structures are formed, but none of there are, suppose there are two resonating structures. None of the structure will give a exact chemical properties of a particular compound. So you can say the resonating structures are not actual structures, but rather the the actual structure is rather a resonance hybrid. Resonance hybrid, sorry, resonance hybrid of different resonating structures. For example, as we had seen, RC double bond OH. Fine. So this is one structure, this is other. So these are A and B, both are two resonating structures, but none of a single structure, either A or B, can express the properties of a particular acid. So if I want to have an actual structure of carboxylic acid, then it will be a resonance hybrid. That means it will be indicated as RCO, and here of partial bonds. This indicates that there is a shifting of electrons. Fine. This indicates that there is a shifting of electrons. And this whole structure specifies the properties of a particular carboxylic acid, or any, for that matter, any molecule. Now, there is something called mesomeric effect. It is also one of the form of resonance effect. Mesomeric effect. Now, what do you mean by mesomeric effect? Well, electrons in a conjugated system, electrons present in a conjugated system either move away or towards a substituent group in a ring, to be more precise, in a ring. Now what? Electron in a conjugated system either move towards or away to a substituent groups. Move towards or away from the substituent group in a ring. For example, we will see this is the benzene ring. This is, that means, and it is bonded to OH. So phenyl ring is bonded to OH. This is known as a phenol. The name of the compound is phenol. Now, OH, it has a lone pair of electrons. So, it will, OH, since it is a saturated, I have told you. So, it will be electron donating. It will donate here. The moment it goes double bond, this double bond will go and fine. This will be minus OH, which will be positive, and this will be, similarly this will has to be here, and this will go here. Resonating structures of phenol. So the resonance hybrid we will indicate as a round and OH. What does this round indicate? Round indicates throughout the electron is flowing throughout the ring. Therefore, it is indicated by a round. Right? Yeah. Similarly, if we want, we can also see for fine. This here. Okay. Now this. Double bond N, O minus, this is plus. Fine. No. Sorry. If you can see in all the structures, the overall charge remains the same. Fine. Overall charge remains the same. 2 negative, 1 positive, 1 positive. 2 negative, 1 positive here, other positive here. Again 2 negative, 1 positive here, 1 positive here. Right? So this and these two structures happens to be same. Fine. Okay. Mesomeric effect. Mesomeric effect basically are of two types. One is plus M effect and the other one is minus M effect. What do you mean by plus M? Means electron donating group attached attached to the ring. Just now we saw the example of a phenol in which OH is an electron donating group. So this is plus M effect. And what is minus N effect? Electron withdrawing group attached to the ring. Let's do this off. NO2. Fine. Which is an electron withdrawing group. And this is an electron donating group. Now, there are few examples of electron अपना plus M effect. Plus M effect groups. Again the same thing. All saturated. When saturated, single bonded, sigma bonded functional groups are attached to the ring. They are known as plus M effect group. For example, OH, OR, alkoxy, then NH2, amine, then I will say NR2 means N bonded to two alkyl groups. Then I will say X, that is halogen. In halogen it is precisely chlorine, because fluorine is an electron withdrawing group. Although the electron donating is very weak, but electron withdrawing group is the main feature of fluorine. But chlorine is a dual. It also has the electron withdrawing ability and also electron donating ability. So depending upon its ability of where it is attached to, with respect to what it is attached, there will be formation of a product. Now similarly I will say minus M group will be the same thing, unsaturated, like NO2, fine, like SO3H, like aldehyde, COH or COR, ester. We will see what is the difference between inductive effect and a mesomeric effect. First difference. This in inductive effect, and mesomeric effect I will write. In inductive effect there is an interaction between a lone pair of electron and the bond electron. Lone pair of electron and bond electron. Okay? And in mesomeric effect, it is due to the presence of functional group. Due to the functional group, there is a shifting of electrons. Shifting of electrons. Between lone pair and the pi bonds. Fine. Second point I can say. It is a distance dependent. Means is distance dependent. It depends on the distance. How far? If it is more than 3 carbon atom, the inductive effect, irrespective whether it is plus I effect or minus I effect, decreases. While in this it operates till the end. Till the end of the conjugated system. Of the conjugated system. Fine? Now, what is the third? There is a displacement of sigma electron. Displacement of sigma electron. Here there is a delocalization of pi and lone pair of electron. Delocalization means the electron is not localized to any precise place or any specific atom. Throughout the system, the electron is rotating. Throughout the system, the electron is rotating. As we saw in phenol, the resonating structures of phenol and nitrobenzene means benzene to which nitro is attached. We saw the structures. If you can see the previous slide, you can see previous. Right? There is a delocalization. Then, second thing, it operates in saturated and unsaturated compounds also. But this operates only in conjugated unsaturated compounds. Fine. Now this inductive effect happens to be a permanent effect. This happens to be a temporary effect because the electron is revolving throughout. So at a particular fixed place there is no electron. So it is known as a temporary effect. Whereas in case of inductive effect, the position of electron withdrawing group or electron donating group is fixed. So it is going to operate throughout the carbon, means throughout the first 3 carbon atoms. So it will be operating to the first 3 carbon atom permanently. The electron will not be moving, right, along the sigma bonds. But in case of mesomeric effect, the electrons are operating, they are revolving around throughout the system from double bond to single bond, again double bond to single, again charge. Fine? Okay. So this much I think so is enough for today's lecture, where we have seen all 2 different types of effect: inductive effect, resonance effect. In resonance effect also we have seen mesomeric effect, and then initially we saw electronic effect. Is what is electronic effect? Fine. Then we also saw the application of inductive effect. If you have any query on this, you can please do write to me in the comment section. I'll be surely obliged to give a reply to it. And last but not the least, I do request you to please share it, follow and like the video, and try to contact me on my either on my Twitter account, or you can also do a WhatsApp to me, right? And I will try to solve your problem. Okay, so I shall take a leave. Thank you. Namaskar. Thank you.